deal. You have this bell work in front of you. See if you can borrow one. I might be able to hook you up later. So you have this bell work in front of you. Look up here, please. So you have a quiz tomorrow. Okay. It'll look just like this bell work. Now on your quiz, you'll have to count how many sig figs are in the first few problems, and then you'll have to do a multiplication and a division problem after that. Let's do a multiplication and division problem together real quick. Let's try this guy. 31.22 times 9.8. 31.22 times 9.8. So plug that into your calculator. 31.22 times 9.8. Don't do the same.
I have 305.
305.
2.956.
Okay. All right. Now pay careful attention. This problem is rather difficult on purpose. Okay, so that's what your calculator will tell you. Let's figure out how many sig figs we're allowed to keep. So, let's see here. I have, how many sig figs in 31.22?
4.
How many in 9.8?
2.
Which one's the weakest link? The 9.8. So the weakest link is 2 sig figs, so you're only allowed to keep 2. So your final answer should only have 2 in it. So here's what your calculator tells you. 305.956. 305.956. You need to round after that second sig fig. You need to round after that 0. So what does that 5 tell that 0 to do? Round up. Now here's a mistake that a lot of people are going to make. They'll put 31. So they're like, okay, because that's 0 rounded up, right? What's the problem with that? What it means is, look at this. This answer should be about 300 something, right? But you just put 31. Those are two completely different numbers, okay? Well, it depends. So you should have, you're rounding, right? Rounding to the closest tens place. Now, what if someone's like, but Mr. P, you just put a third digit there, so you're kind of on the right track. You put a third digit there, isn't that a 3 sig figs? What's the problem? The 0 doesn't count. The 0 doesn't count because there's no decimal. They couldn't do this, because that would make that 0 count as a sig fig. But as long as they just write it as 310, that's a trailing 0 with no decimal, so we're all good. And of course, the model student would box that up. So, tomorrow on your quiz, let me take a look at it. The first 5 questions are just asking you how many sig figs are in this number. That's it. The next 4 questions, you have 2 multiplication, 2 division, and you need to calculate it like this and circle your final answer, okay? So you got 9 questions tomorrow. This bell work is a longer and more difficult version of your quiz, so if you can do this bell work well, you should be in good shape. If you're watching this video, the answer key is below the video, and if you're in person, I'm going to drop a purple answer key off on your desk here in a minute. I know a few of you guys have some questions, but go ahead and get cooking on this bell work. I'll be coming around.
All right, folks. So you have just taken sig figs last week, and now we're going to move on to density, baby. We will be maintaining our sig fig calculation rules while we're doing density problems, just for the record. But that's what we're moving on to this week, density. Now let's start with the equation. So D for density here is equal to M, which is mass, over volume. I think some of you guys have probably seen this equation before. Density equals mass over volume. Now just a little fun way to remember this. I'll do this in pink here. Okay, a fun way to remember it is that D equals M over V. And if you look at that, it looks like a heart. You guys, I love density. Oh my gosh. So there you go. Amazing. Let's go ahead and continue. All right. So density, to give a more verbal definition, density is the amount of matter in a given space, aka volume. So you can use the word space and volume interchangeably during this unit. So density is the amount of matter, or how much stuff do you have in a given space? How much stuff do you have in a given space? So if we look at these 2 boxes here, this box on the left has a few purple dots in it. The box on the right has a bunch of purple dots on it. Now they have the exact same space or volume. So this black box these purple dots are in, they're identical boxes. Okay, so these boxes have the exact same space or volume. On the left here, though, we have less matter, you could say mass. And on the right, we have a lot more matter or more mass in the box. So what that leads to is this box on the left is less dense than this box on the right, which is more dense. And sometimes you want to plug in some random numbers to kind of think of it this way. So let's say this one has a mass of 1 inside the box, and the space is a volume of 10. Okay, so remember density is mass over volume. So this would be like a 1 over 10 density. Whereas this guy over here has a lot more mass. So let's say it has a mass of 10. And because its space is exactly the same, its volume will still be 10 just like the other box. And so you can see how the density on the right is a lot higher than the density on the left. And why is that? Well, even though their space is the same, the box on the right has a lot more mass, a lot more matter in it. So it is a physical property. Density is a physical property. And it is intensive. Intensive. Intensive means that it does not change with more or less of the substance. So when you have an intensive property, it doesn't matter how much of the stuff you have, the property does not change. Okay? So for example, if I were to take a piece of paper here, so I'd be like, what color is this paper? And you'd be like, white. Be like, okay. Now I only have a small piece of paper. What color is this? You'd be like, white. What color is this? You'd be like, still white. The idea is it doesn't matter how much of the paper I have. Color is an intensive property, and it'll be white no matter what. And density is the same. It doesn't matter how much of the substance you have. Density does not change because it's an intensive property. All right, now we're going to start getting to demos in this video. So I'm going to do a few demos involving aquariums and cans of pop. Now going into this, I want you guys to know something. That the density of water is exactly 1.00 grams per milliliter. The density of water is 1.00 grams per milliliter. And we're going to make some conclusions about diet pop, regular pop, and salt water, knowing that fact. All right, folks. So now what we're going to do is we're going to do some demonstrations with these tanks. Got a couple of tanks of water here, and we're going to see what happens when we drop some pops in there. Now I'm going to zoom in on this tank on the left. Yeah, baby. Here we go. Up, the cord's caught. No. All right, there we go. Got the tank on the left here. So, what's going on? Well, I guess this would be your right, my left. Whatever. This tank. All right, so I got a can of Coca-Cola. Woo! Makes me think of the polar bear. Let's go, baby. What's going to happen when we drop this in here? Ready? Oh, my gosh. Oh, my gosh. Up, up. Oh, it sinks. All right, well, whatever. So Coca-Cola sinks, but what about Mountain Dew? Ride the dew, do the dew. Okay, sponsored by Lunchables. No, I don't know. I don't even know what I'm saying. All right, here we go. Check it out. The dew. It's going to float. Oh. Well, it just sinks. All right. Well, whatever, man. What about Diet Coke? Let's talk to me about Diet Coke, baby. Here we go. And, oh. Well, hello. Now we're floating. Now we're floating. You know, just kind of, all right, just stay down there. I said stay. Hey, get down there. Well, Mountain Dew is a lot sweeter than Coke. What if I have a Diet Mountain Dew? Diet Mountain Dew Zero here. See, it says Diet. Yeah. All right, well, this will sink. Boom. And up. Up she goes. What? Craziness. All right. All right. So we got the regulars sinking, the diets floating. Now, what if we come over here? Bop, 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 bop. Yeah. We're into the other tank here. My right, your left, whatever. Let's do this all over again. Okay. So now what's going to happen with the Diet Coke? Now what's going to happen with the Diet Coke? Here we go. Yeah. Oh. Well, all right. Still floats. Cool Diet Coke. What about the Diet Mountain Dew? Here we go. Blast off. Yeah. All right. Sweet. Looking good. Well, all right. So the Diet Coke floats still. So let's see here the Coca-Cola. Let's go, baby. And whoa. All right. So now all of a sudden Coca-Cola's floating. Wait. Hold on a second. I'm gonna take this out. I'm gonna put it in the other tank. Is it broken? What? Why is it? It sinks over there. You come over here. What the heck? The Coca-Cola's broken. All right, but Mountain Dew will take care of us. Let's go, baby. And yeah. What is going on? What is going on? Okay, they sink, they float. What? Their boat just tanks of water. What's going on? Hey, does my face look funny if I look at you through here? Does that look crazy? I can't tell. Hello? All right, let's debrief on the smart board. All right, so we just watched those demonstration videos, and here's some of the things that we learned. Okay, so the Diet Pops, they always floated in water. And since we know that less dense things float in more dense substances, that means that Diet Pop must have a density that's less than water's 1.00 grams per milliliter. And typically speaking, Diet Pop has a density of about 0.98 grams per milliliter, and that's why they float. We also saw that regular pop sank in regular water, and so regular pop must have a density that's greater than 1.00, and they will typically have a density about 1.0 grams per milliliter. And then we saw that all pops, Diet Pop, regular pop, they all float in salt water. So what does that tell us? Well, that tells us that salt water must have a density that's higher than all of these. What exactly is this density? Well, I'm not sure, but I know it has to be more than 1.10, which is the density of regular pop. We found that the salt water I used today was about 1.18 grams per milliliter. All right, now why does this make sense that Diet Pop is less dense than regular pop? Well, here, this is 1 gram of Sweet and Low, and this is a potential sweetener in Diet Pops, okay? So there's not a lot of mass in this little baggie, but 1 gram of Sweet and Low in terms of sweetness is a rough equivalent of 180 grams of sugar. Do you see how there is way more mass in this baggie than there is in this baggie? Okay, that's why the density of regular pop that uses sugar is a lot higher than Diet Pop, which can use something like Sweet and Low. So if we were to sort of draw that in these two different cans, okay, so let's say that this can on the left here, let's say this can is Diet, and the can on the right is your regular. There we go. So the Diet Pop maybe has, a density that kind of looks like this visually. But then the regular can of pop, where it has 180 grams of sugar to compare with the 1 gram of Sweet and Low, might look like something like this. Yeah. This isn't obnoxious at all. Yeah. Okay, so even though these cans are identical, and I did copy and paste my poor drawing of a can here, so they have the exact same volume, but the regular can of pop has a lot more mass in that same space, in that same volume, and that's why regular cans of pop are a lot more dense than Diet cans of pop. All right, so now what you're going to see is a awesome demonstration using graduated cylinders and a pretty pink little golf ball. I have 3 identical pink golf balls. So you're going to watch that, and then we're going to debrief here. All righty, you nerds. Can you see me? Oh, it's like dodging. Oh. All right. So now I got 3 identical graduated cylinders full of liquid, and I got 3. Oh, wow. I almost knocked that one over. That was crazy. Oh, that's the one I really didn't want to knock over, too. Well, anyways, I have 3 graduated cylinders and 3 identical golf balls. Here we go. Pink golf balls. Let's see what happens when we drop them in. Graduated cylinder number 1. Will it sink or float? Sink or float. Here we go. Up. There we go. Look at it. Oh my gosh. Oh my gosh. Will it make it all the way to the bottom? Find out next episode. Dink. Well, it sank all the way to the bottom. All right. Let's try this next one. Here we go. Let's watch her sink. And sink. You're supposed to sink. All right, hold on. I think it just broke it. Give me a second. All right. Just going to go ahead, smash this down with the ruler. There we go. Yeah, okay, there's what you're supposed to do. Okay, sweet. There we go. Nice, so you can see that it's sank. What are you doing? Stop! Stop moving! Stop, what are you doing? Hey, are you listening to me? You're not listening. You're blowing past the stop sign. Well, I don't know what's going on there. That one floated for some reason. All right. Third time's a charm. So maybe you said float on the first one, then you said sink on the next one, so you've been wrong both times. But what about this guy? Let's see. I'll put him up front here. What about this guy? Well, no, I'll just put him back here. Who can say? All right, you ready? And here we go. Up. It's a sinker. There he goes. Okay, so you can see this guy sank all the way to the bottom. And what? What are you doing? Are you sinking or are you floating? What is happening? Is this some sort of sorcery, Mr. Pilcher? What is going on? How can it float? And then how can it sort of float, sort of sink? What is going on? Okay, so here's what happened when we dropped those golf balls into the different graduated cylinders. Okay, so golf ball number one. Oh, what? Well, whatever. Golf ball number one. I'll go ahead and copy and paste that a couple of times. There we go. Golf ball number one was like and sank to the bottom of the graduated cylinder. Golf ball two, I plopped it in here. It was like boing, and then just sort of sat at the top of the graduated cylinder. Golf ball number three, I plop it in there, and you're like, is it going to sink or float? And it's sinking, it's sinking, it's sinking. What? It sank, float? It soated? It flanked? What? Wait, what? What the heck is going on here? Okay, so let's think about what we know for sure. In the first graduated cylinder, I don't know what's in that graduated cylinder, but I do know that the golf ball is more dense than whatever liquid is in that graduated cylinder. And in this first one, we actually had water, okay? And that density is 1.00. So we know that the golf ball has a density that's more than 1.00 grams per milliliter. In the second graduated cylinder, the golf ball floated. So that tells us, like, okay, so the golf ball might have a density greater than 1.00, but it must be less than whatever liquid is in this time. And in this second graduated cylinder, we had some high quality salt water. So this particular salt water's density was probably about 1.10 grams per milliliter. Okay, so we know that the golf ball's density is somewhere in between 1.00 and 1.1 grams per milliliter because it sinks in 1.00 water, but it floats in 1.10 salt. But then here, you're like, wait, what the heck? Why is it magically floating in the middle? Well, what I did was I poured in some salt water. I filled this thing up about halfway before I started the video. So down here, we had your salt water. And again, that density is about 1.10 grams per milliliter. And then very carefully, I poured on top of that some regular water, which has a density. So I got my regular water there, density of 1.0. Wow, the E in water is not looking so good. There we go. And so the golf ball, which has a density of around 1.05-ish, give or take, it sinks through the water layer, but then it floats on top of the salt layer. And it looks awesome because you can't really visually see the difference between the water and the salt water I have in there, so it looks like it's just sort of magically floating. But that's what's going on. And one demonstration, or one thing I like to sort of show my students, okay, think of it this way. So I'm going to go ahead and erase this down here so I can move this guy. if I were to take this graduated cylinder and take this one and put them on top of each other, see how the golf ball would end up in the middle, right? And that's because you have water on top and you have salt water on bottom. And so, of course, that would cause the golf ball to float in the middle. So that's actually what's happening in that last one here on the right. We just have the water and the salt water in the same container. Craziness! So I don't know about you, but I'm definitely going to be posting this on the Insta tweets and the Facegrams. Going to tell everyone about it. Grandma, Auntie, my dog Bessie. This is an amazing demo video. Mr. Pilcher blew my mind. We're moving on. We got to talk about ivory soap and a microwave. Now, ivory soap, boom, right here. You can buy it at the Kroger's on Maxtown. So if I go ahead and open up this bar soap, okay, here she is. Oh, this one's got a little, oh, yeah, here it is, and it says ivory. There it is, boom, beautiful. Now, the story goes, back in the day, they used to have these bars of soap. But then, this genius engineer or someone of that nature was like, wait, guys, wait a second. I have a brilliant idea. Okay, so how about we start putting a bunch of bubbles in this soap bar, okay? It'll do a couple of things for us. Number one, we can sell less soap for the same price because people won't know there's holes in the soap. And number two, the soap bar, if we put air holes in it, it'll become less dense than water and it'll start to float. So we can be like, people, look, we got this amazing new technology, bars of soap that float, all right? And people are freaking out because back then they didn't have the interwebs to see cool videos like Mr. Pilcher's demos with salt water. So they were freaking out about bars of soap that could float. And so this engineer got a sweet marketing idea, but he also saved his company money because they were giving people less soap for the same price. Now, if I take this bar of ivory soap and I cut a little chunk off, create a mess all over my desk, boom. So if you can kind of see in here, there's like little holes, little pockets all throughout this soap. Okay, those are little air bubbles. Now, one thing that's really fun to do is to put this soap in a microwave. I'm going to go do that right now. All right, kids. Now I'm going to prove to you that this soap actually does have holes in it, right? So if I take this soap and I put her in a microwave, see how big that piece is? Okay, not that big. A little bit bigger than my thumb. If I put that in the microwave, okay, what should happen is if there truly are gas bubbles in there, then the gas bubbles will expand quite a bit. And so let's see what happens. I'm going to go ahead and time cook. Let's cook this turkey. Here we go. All right. There it goes. We're cooking. And we're cooking. Let's see here. Oh, yeah. Nothing is happening yet. Amazing. Amazing. All right, let's see. Oh, we're getting something to happen. Oh, my. Oh, my. Like, Mr. Pilcher, I can't see anything. Why are you showing me this video? Oh, yeah. Oh, there she is. Look at this turkey. Oh, yeah. Look out. Oh, I just spilled it all over the place. Craziness. Boom. This is your soap. Oh, that's toasty. All right, guys, check it out. Hey, guys. So I used to have this addiction. It's really embarrassing. I used to have this addiction. I was addicted to soap. I couldn't stop. I needed soap in my life. But don't you worry, because I'm clean now. You get it? I'm clean now!
Density equals M over V. The M stands for the amount of matter or mass. You absolutely want to write this down. The V stands for amount of space, or you could say volume. So mass and volume, matter and space. The little triangle here, by the way, some people like to use that puppy. We have density, volume, and mass. All right. So if we fill out this little box, M, as I mentioned, stands for mass. Its units are grams for the little g. You gotta know all these for me.
Is it matter?
You can say matter or mass, either one. Most of the time, we'll actually say mass. The V in volume, that stands for two different things. If we're talking about a liquid volume, it's milliliters. If we're talking about something solid volume, we're talking about centimeters cubed. So what I have highlighted is what you definitely need to write down. Mass. Because remember, when you get the volume of like a cube, it's length times width times height. Centimeters times centimeters times centimeters, centimeters cubed. That's where that comes from. So that means if you have a density of a liquid density, it's going to be in grams per milliliter, because liquid volume's in milliliters. Whereas a solid density is going to be grams per centimeters cubed. Grams per centimeters cubed. So those are different units that we'll be looking at throughout the density portion of Unit 2. Better? Alrighty. So, one more thing for the notes before we do a practice problem. I would like you to know that 1 milliliter, you need to know this, is equal to 1 centimeters cubed. So you can convert the two. 1 milliliter is equal to 1 centimeters cubed. They take up the same amount of space. But milliliters are for liquid, centimeters cubed are for solids. Now let's try one of these problems together. A block of aluminum occupies a volume of 15.0 centimeters cubed. So we're given the volume as 15.0. The mass is 40.5. Make sure you follow along with me. The density is what we don't know. So I put a question mark there. I don't know what the density is. I don't know.
You can multiply the volume with the volume.
If we remember our equation, density is mass over volume.
Oh yeah, so you
Just do your mass over your volume. In this particular one, so density equals mass over volume. So 40.5 over 15. Now if you plug that into your calculator, what are you going to get? 40.5 divided by 15. Divided, yeah. I see what you're thinking, multiply, yeah. 40.5 divided by 15 is 2.7. Wait a second though. How many sig figs does 40.5 have?
3.
Uh-huh. Let me finish this up and then you can go in a minute. How many sig figs does 15.0 have? How many sig figs does 2.7 have? 2. So we need to have 3 though, right? So what are we going to do with it, Samaya? You need to add that trailing 0, which is significant when there's a decimal. So you got to give me your final answer as 2.70 and make sure you have the proper units. Okay? We had grams, and the volume is centimeters cubed. So you should have grams per centimeters cubed. Was there a question over there? You're all good? Okay. Are there any questions for me before we wrap up this lecture? Okay. You have a couple more problems on that worksheet. Here's the thing. On your density quiz next week, I will ask you, this is a promise, I will ask you to solve for the density at times, but at others, I'll ask you to solve for the volume, or I could ask you to solve for the mass. You need to be able to solve for all 3 of those. So don't forget your triangle here. If I want to solve for mass, so if I cover up mass, what do I have to do? Density times volume, if you ever use one of these. If I had to solve for volume, what would I do? Mass divided by density, okay? So make sure you can go back and forth between those 3. You got a couple more practice problems. We'll go over them towards the end of the period. Get them cooking for me.